Okay, guys, let's take a look at today's lesson. Let's see, we've talked about polynomials for a few days now. The first day, if you recall, we worked on graphing polynomials and zeros. Yesterday, we divided polynomials and looked at all kinds of interesting and fun ways to divide polynomials. Today, we're going to look at polynomial applications, word problems that have to do with polynomials. And we're going to be using the calculator throughout the whole lesson, so hopefully you have that with you. All right. This actually helps us in our work next year in calculus because the procedures that I take through for solving problems are just like the procedures we do in calculus. We're going to draw a diagram, we're going to label it, we're going to find relationships between the variables, we're just going to kind of work through the word problems. So let's kind of read this one. So we have a rectangular parcel of land that has an area of 5,000 feet squared. A diagonal between opposite corners is measured to be 10 feet longer than one side of the parcel. What are the dimensions of the land correct to the nearest foot? Okay, so first thing we're going to do is draw the diagram. Okay, so we got a piece of land. It talks about a diagonal, so we need to put that in there. You can use whatever variables you would like. I used x here and y here. So let's see. So the area is 5,000 feet squared. The diagonal between the opposite corners is measured to be 10 feet longer than one side. Okay, it doesn't really matter which side you pick to make 10 feet longer. It makes no difference. You could pick X or Y. It doesn't matter. I decided to pick X. So I have X plus 10. Alright, 10 feet longer, what are the dimensions? So let's see what we have going on. We need a relationship between all those variables. Since these variables exist on all the sides of a right triangle, Pythagorean Theorem probably kind of pops into our head. So let's go ahead and write that out. So we would do x squared plus y squared equals x plus 10 squared. So we have variables x and y there. Kind of keeping in mind we're going to be using a calculator. I think we could probably fairly easily solve for y. That doesn't seem to be a bit of a problem. So let's go ahead and do that just to kind of get ready. Let's go ahead and solve for y. So we get y squared equals, we're going to FOIL this out. So x squared plus 20x plus 100. Then I'm going to move the x squared over, so minus x squared. Okay, so let's keep cleaning that up. See the x squareds go away, and we have y squared equals 2x plus 100. Now I am going to square root both sides. 20x plus 100. I am going to square root both sides, but we're mathematicians, right? We know that it's a plus minus, but we're dealing with distances. So really the negative radical wouldn't make sense in this case, right? It wouldn't make any sense. So I hope it doesn't trouble you too much, but I'm just going to use the positive radical. So y is going to be the square root of 20x plus 100. Okay, so we're not really sure what to do with that yet. Let's go back and keep investigating the problem. Let's see. So we want dimensions of the land. We have to use this information because right now all we have figured into this equation is that 10 feet longer part. We don't have any other restrictions on it. But there are restrictions. We know the area is 5,000 feet squared. It's not bigger or smaller than that. So let's think about how would we find the area of this land. We would do, the side times side, right? X times y. So we have xy equals 5,000. Okay, so that's pretty good. This gives us some more restrictions. So let's think about this for a second. We have a representation for y, which is right here. This is what y is supposed to be with the restriction that we have on this, 10 feet longer thing. This is y. And this is x and y with the other restriction. Why don't we use this equation and substitute in this y in this equation? That allows us to bring them together into one equation that we can work with. So we're going to use this equation. So we have x times y, which is the square root of 20x plus 100, equals 5,000. Okay, Is everybody okay with that? So this is the point where we're going to go to our calculator. So I actually need to erase this. Does everybody have what they need? We're gonna go to my calculator. And I'm gonna show you how I would solve it, which is probably much like you would as well. We have options, but let's go to the calculator. What I do is I put the left side in y1 and the right side in y2. That's just how I solve equations on the calculator. So we go to let's see. I'm gonna put 5,000 in y1 and in y2 I'm going to put x times square root of, what do we have? Square root of 20x plus 100. 20x plus 100. Now, I prefer to mess with the window myself. I really encourage you to think about the window as you're graphing. With some equations, if the window is like set by 10 by 10, which is our normal window, it's like, what's going on? We can't tell. So I encourage you to think about adjusting the window. Our y value is way up at 5,000, so I'm going to change my y maximum to, like, I don't know, it's up at 5,000, so say 5,500. And with such big numbers as that, it's probably very likely that our x value is going to be bigger than 10. So, I don't know, why don't we make it like 150 or something? And let's see if we can see what's going on. Okay, so let's graph it. Okay, good. So where the two equations cross, that's where our solution is. That's the value of our answer. So let's just do our intersection. So second trace. Number 5 is our intersection. And just because, I'll make sure we're clear, you can change the equation that you're on by pushing this up-down arrow. If I want to be on that equation or that one, I can just go back and forth. It probably would be faster to move along that, horizontal line. So I'm going to go there and move to the intersection. And then we hit enter, enter, and then enter. Okay, so what that tells us is the x-coordinate, basically our x value on our little rectangle. And it says, what are the dimensions of the land correct to the nearest foot? So we really need to pay attention to what the directions are saying, right? Because if we don't, that kind of can bite us. So here we're going to the nearest foot. So for this, it's just going to be 106, right? 106 feet is what x is going to be. So let's go back to that example. So x is 106 feet. We need to find the other dimension. If you recall, we had a relation. There's a couple of relationships between x and y. You can really choose whichever one you want. I'm going to go back to this relationship that we had, xy equals 5,000. And so I need the y, so I'm going to do y equals 5,000 over 106. And I would leave the decimal in there, round at the end. And I'm going to get 47. So y is 47 feet. So our dimensions are 106 feet by 47 feet. Okay, is that one okay? All right, we have a couple of other examples on the next slide, so let's go to that. All right, number 2. Says a fuel tank consists of a cylindrical center section 4 feet long and 2 hemispherical end sections. All right, so I am not going to try to draw this in 3 dimensions. I'm going to draw the cylinder as a rectangle. So here's the cylinder. By the way, it's pretty important to have a diagram to look at. I encourage everyone to draw a diagram. We don't want to leave that out. And it has 2 hemispherical end sections. So basically, if I'm drawing the 2-dimensional version, that's just a semicircle. Or it's going to have like a semicircle on each end. Okay, so envision that. That should be a 3-dimensional figure. It says the cylindrical section, so this part right here, this distance right here is 4 feet. Okay, so cylindrical center, 4 feet long, 2 hemispherical end sections. Great. So part A says express the volume of the tank as a function of r, the radius of the tank. Okay. So it's actually important for you to know the volume formulas. You know, in calculus, we have to know the volume formulas. They don't give us those. So if that's something that you don't know, you need to know, because I'm not going to give you volume formulas. Alright, so if we're doing the volume of this figure, it's going to have to be the sum of two different kinds of figures, right? We're going to have to take the cylinder, volume of the cylinder. Now let's think about this. We have two hemispheres, so if I were to put that together, it would be just a sphere, right? So I'm going to add the volume of a cylinder and a sphere. That's going to be my volume. So volume is going to equal, so recall the volume of a cylinder. It's the area of the base times the height. The base is a circle, so it would be pi r squared h plus the area of a sphere. You may or may not remember, but you do need to remember. It's 4/3 pi r cubed. Okay, 4/3 pi r cubed. Now looking at this equation, we know we're going to have to go to the calculator, and I have too many variables. I've got an h and an r. Well, and the v would be like the y. So let's see if we can get rid of one of them. Actually, we can. The cylinder, we already know the height of it, right? It's already told us the height of it's 4. So I'm going to replace the h with the 4. And that will kind of clean it up, and we should be able to work with that. So 4 pi r squared plus 4/3 pi r cubed. Okay. So that is part A. Express the volume of the tank as a function of r, the radius of the tank. Okay, good to go. Okay, part B. If the tank has a volume of 100 feet cubed, what is the radius of the tank? Okay, so if the volume is 100 feet cubed, so I would say 100, replace v with 100, equals 4 pi r squared plus 4/3 pi r cubed. Here's where we go to the calculator. Okay, what I would do is I would put 100, the left side, in y1, and I would put this in y2, and I would intersect them. Now we're probably going to have to mess with our window because it's quite large from the previous example. And if we're okay with that, the other one I did was exactly like that. So I'm not going to go to the calculator on this one. Exactly like we did before, left side in y1, right side in y2. And when we do that intersection, we should get r to be 2.1525 feet. Let's talk about rounding. Really important. On the AP test next year, if you don't round properly, you lose a point. And we don't want that. We want to just program ourselves. We're always to the thousandths unless we're told otherwise. So in a case like this, when we are allowed to round or truncate, those are both acceptable. When we have two different possible answers, I typically go to the 10,000th so you can judge, so you can see which one you would have had. So our two answer options would be, we could say r equals 2.152, which would be truncating. We just chop it off after 3 decimal places. Or we could round it, and it'd be 2.153. So those would be our two possible answer choices for that problem. Okay, we okay with that? All right, let's look at the last one. We have a cylinder is inscribed in a sphere with a radius 5. Okay, I'm going to stop right there. We're going to draw that picture. So we have a cylinder inscribed in a sphere. For the sphere, I'm just going to draw a circle. I'm not going to attempt to draw a sphere. So we have a circle. Okay, there's the sphere. And we have a cylinder inscribed in it. Okay, so instead of me trying to draw a cylinder, I'm just going to do the two-dimensional, like a rectangle. Okay, that's my cylinder. So here's the cylinder that's inscribed inside. And the sphere has a radius of 5, so I'm going to go to the center and draw to this edge where both the corner and the outside meet. I think that's most convenient, and that's 5. Alright, so we have that part done. Let's see what else they say. Express the volume of the cylinder as a function of x. And they tell us what x is. We don't get to pick what x is. X is the perpendicular distance from the center of the sphere to the top of the cylinder. Okay, so if I go to the center of the sphere to the top of the cylinder, that distance is x. Okay, that's what x is. We don't get to pick. So we need to write the volume of the cylinder as a function of x and give the domain. Okay, so let's work on, let's just write the generic formula for volume of a cylinder. We just talked about it. V equals pi r squared h. Okay. Alright, so of course the r has to go and the h has to go. They have to be only x's there. It told us to express the volume as a function of x. Alright, so let's work on this relationship right here. This actually is r. You know, if we pull this out, make it a little bit bigger so we can see. That's x. That's r. That's the radius of the cylinder, would be that top part right there. And that's 5. So we do have a relationship that we can establish between those variables, right? That's on our right triangle. So we can establish the relationship of Pythagorean Theorem. So let's do that. So we have, let's see what, x squared plus r squared equals 25. I really want to get rid of the r squared up here, so I'm going to solve for r squared. So r squared equals 25 minus x squared. Okay, fantastic. Let's start our new volume formula over here. So instead of r squared, we're going to put this part in. This 25 minus x squared. That we can substitute that in. So 25 minus x squared. Okay, great. Now we have the problem of the h. We need to figure out how to get rid of the h. So this right here is part, this distance right here is x. If we wanted the distance or the height of the whole cylinder, couldn't we just double that? Right? That would be the same, right? So my height is actually the same as x, 2x's, right? 2x. So I'm going to replace h with 2x. And now we have expressed the volume as a function of x. You can multiply it out if you want to. You can leave it factored if you want to. It doesn't matter to me, whichever you prefer. I'll just leave it factored. Why not? Let's just leave it like that. Okay, so that's our volume. Now they want us to give the domain. And this is a thing that we do in calculus as well, and it really troubles some students. They don't really know how to find the domain of that. So let's think about it. The easiest way to find the domain when you're dealing with a real-life problem like this is to leave it factored and see what would cause each factor to go to 0. Because we know we can't have negative volume, right? We can't have negative volume. But if I look at this factor, I know if x was 0, it would cause the volume to be 0. So we're going to start out, we can't actually equal 0, because if we equaled 0, there wouldn't be like a figure, right? There wouldn't be any volume. But if it was like 0.1, I mean, we'd have volume there, right? So now let's look at the other side. How big could we make it? Let's see. So if we look at this one, what would cause this factor to go to 0? 5. So let's talk about, I want to talk about why those numbers are the right numbers. Let's look at the 0 first. If I was smaller than 0 here, like a -1, that would cause my volume to be negative, wouldn't it? That'd be a problem. Or if I was bigger than 5, like if I put a number in here bigger than 5, like 6, wouldn't that cause this to be negative and my volume would go negative, and that would be a problem? So that's how we find the domain. That's the easiest way, is to think about, in factored form, what would make each of those factors 0. And so that gives us our domain. Okay? That's part A. Let's look at part B. Part B is asking us to find the value of x that maximizes the volume and find the maximum volume. Okay, this is going to require a calculator. I'm actually going to go to the calculator. This is a little bit different than the other calculator one that we did. I'm going to put this in the calculator, actually exactly like it looks, just like this, in the y equal. So does everyone have what they need off of here? Okay, so I need to erase. So let's go to our calculator one more time. right, we're going to go to y equals. Let's clean that out. And I'm going to put our equation that we got, which is pi, and then open a parenthesis, 25 minus x squared, close parenthesis, and then we had, what, 2x, close. Okay. So the window that we had previously was gigantic. This probably, we don't really need that much of a window. Let's see, we've got, let's go in and let's just adjust it. I'm going to take this down to, instead of 5,500, just 500. Hopefully 500 is enough. 500. And with that, you know, I'm not going to need 150 x's. That's probably not going to be necessary. So let's go back down to 10 and see if that's enough for me to see. So let's graph it. And it does. That fits the window. I'm looking for maximum. So I'm going to use my max finder. Right? So we go second trace. Our maximum is number 4. Then we're going to scroll to the left of the maximum. And then we're going to scroll to the right of the maximum and hit enter. And this actually gives us our answers, both answers that it was asking for. It was asking for the value of x that maximizes the volume. Well, that's right here. And so it could either be 2.886 or 2.887. So let's write down our two options here. So x could be 2.886 or x could be 2.887, depending on if you want to round or truncate. And what unit are we in? Did it give us a unit? Nope, sure didn't. Okay. So now the volume is this number right here. So the volume is 302.299 if you want to truncate, or 302.3 if you want to round. And I know that bottom one would trouble some of us because we're like, wait a minute, that's not to the thousands, but it actually is. All right, so how is that? Are we okay? Everybody good?